Hey everyone, welcome back to physics. This will be lecture 25 of the course. And in this section, we're going to continue with our discussion of work and energy. And we're going to specifically look at how to handle work where the forces involved are not constant, so varying. So let's go ahead and jump into it. We'll call this section 5.2 work and energy with varying forces. So in the previous section, we looked at work done by a constant force. But what if the force being applied is not constant? Okay, so the classic example is a spring. Okay, so with a spring, what do we got? Let's talk this through. So I've got some kind of a base that the spring is attached to, and it extends out of this thing, right? Just pretend that's a spring, like a slinky, right? And so all springs have a natural resting state or an uncompressed state. So we'll call this the natural state. Okay, and during the when a spring is in its natural state, it is exerting no force, right? So the force is 0. Okay, now when a spring is either compressed or stretched, we'll take the case of compression, then it's kind of squeezed down, right, into a smaller length, right? So the natural state has a certain length, and when we compress the spring, it gets shorter. Okay, and so when you compress a spring, the force the force is greater than 0, right? So it has some kind of a force. It wants to get back to the natural state, and so where there was previously no force, there is a force, right? And the same kind of thing is true for springs that are stretched. If you stretch a spring beyond its natural state, there's a force required to do that, and the spring will exert a force in an effort to get back to its natural state. Okay. So when compressed, a spring's force is significantly larger. In fact, it goes from 0 up to some positive value. Now, as the spring returns to its natural state, the amount of force it exerts is going to decrease. Okay, right. So let's think about visually the difference between a constant force and something like a spring force. So for a constant force, if we want to kind of plot this, we'll say we've got a force, and then we've got some kind of a displacement. Okay, and so for a constant force, the force is just constant, isn't it? It doesn't vary across the displacement. Okay, but for a variable force, right? Same picture, same plot. So you got the force and the displacement. For a variable force, maybe the force does vary over the displacement. This would be the example of like a spring. Okay, so if the starting position for the spring is a compressed state like this, then the force is going to be very high. But as the spring expands outward, the force it exerts is going to diminish. Right? So this is an example of a variable force like a spring. Okay. Now, when we think about work in this context, we know that work is equal to the force times the displacement. Okay, so if this is the displacement, maybe we'll say from maybe 0 up to this spot, then the force is going to be this constant height times the displacement, which is this distance. And so we see that the work is actually the area of a plot like this. Okay. And in a similar way over here with the variable force, maybe the displacement goes from 0 up to this S value. We can see that area there is also the work, right? So the work done initially to get the spring, the work done initially is larger than the work that's done over intervals later on in the displacement. Right? It varies. Whereas here, the work is constant across the whole thing. So clearly when we're calculating an area like this is just, multiply. It's just the product of these two values. But when we want to calculate an area like this, what do we have to do? Well, we have to use calculus. So we need to integrate to calculate this area. Okay, and it's actually pretty simple to, when you think about this. I mean, of course, you can make it complicated, but let's just draw this out. Okay, so I've got my displacement and my force plot here, and let's say that my force is a decreasing, has a kind of a decreasing nature like this, right? And let's say I want to know the work done over this displacement, so maybe from x1 over to what we'll call x2 over here. So what I can do is I can break this up into into a partition, and I can call this delta x1, delta x2, delta x3, delta x4, right? And just pretend those are the same width. They need to be the same width, right? And then I can come in here and I can break up the area, and I can approximate it, right, using integration techniques, right? So kind of approximate it with the rectangles that are built on this partition, this delta x partition, right? And so if I did this and I calculate this area, and then I add to it this area, and I add to it this area, and then this area, then I get an approximation for the work, right? An approximation for the area would be like f1 delta x1, so f1 being the height here. So this would be like f1, and then plus f2 delta x2, right? Where f2 would be like this, and then f3 would be here, and then f4 would be like here, right? So, right, this is just a sum. It's like a sum product, right? But of course, this is a pretty crude approximation, so what I would want to do to make the approximation better is to make the partition finer, and then finer again, right? And then finer again, until the width of the representative rectangles is extremely small or arbitrarily small. And so as the width of the partition goes to 0, this sum gets better and better, and it's, in fact, we say that as the partition goes to 0, the work equals the integral from x1 to x2 of f dx. Okay, and so that's really this is the work being done by a non-constant force that, of course, is perfectly aligned with the displacement vector, so we're not going to introduce any complexities there. We'll assume that the force is aligned with the displacement vector. And when that's the case, it's an integral like this. Instead of a product between two values, it turns into an integral, right? Because you have to sum over this varying quantity. Okay. All right. And so this is work when the force involved in the work varies across the displacement. Now, it turns out that this formula works just perfectly fine when the force is constant, right? So let's think about it here. Let's crank out the formula, x1 to x2, integrate from that over that range, f dx, right? So if I assume that f is a constant, then the integral of a constant is just f times x, right? And I have to do that from x1 up to x2. And when I do that, I get f times x2 minus x1, which is just f times, what's x2 minus x1? That's delta x. You could write it like that. Or you could write f times s. S being the displacement, right? The distance. Okay. Right, and so this formula works for constant forces. All right, so we just introduce work using this f times s because it's frequently easier to work with if the force is constant than having to think of everything as an integral. But it turns out it's all the same thing, isn't it? Right? As soon as the force starts to vary, then that simple product just turns into an integral. Okay, so that's the idea behind work when the force is variable. Now, we're going to use this section as a good way to kind of introduce the idea of springs and Hooke's law and such. So let's take a closer look at springs, and then we'll do some examples. So again, with springs, you have kind of a natural state. You've got a natural state. And we already talked about springs that are compressed. So what about springs that are stretched? Let's say I take this spring and I stretch it out more. So I kind of pulled it a little bit further than it wants to be pulled, right? And so really I've stretched it out, whatever this value is here, this distance x. All right, so if I pull the spring some x distance beyond its natural state, to keep it stretched that distance, I have to apply a force F. Right? I have to apply some force. And what's been found experimentally is that the force that is needed to keep a spring stretched x distance is proportional to the distance that the thing is stretched. Right? So to keep a spring stretched x distance, I have to apply a force. Okay, to keep a spring stretched x distance, I have to apply a force, right? That force is proportional to the distance the spring is stretched. Right, meaning that it's a simple constant times the distance. Okay, this is Hooke's law. Hooke's law, right? So Hooke's law says that the force is equal to k times x. So x is the distance the spring is stretched beyond its natural state, and k is this this constant of proportionality. Right, now k is going to vary dramatically depending on the spring. Right, so some springs have a very small k and other springs have a very, very large k. Right, so an example would be like a slinky. This is like a children's toy slinky. It's basically a spring, and for a slinky, k might be 1 Newton meter. Very small value. It could be much smaller even. And another example would be like the springs that are used in the suspension of your car. So a car spring, like a suspension spring. Obviously much stiffer than a slinky, right? So in this case, k might be something like 10 to the 5th Newton meters. Something like that, right? Much stiffer. Okay. But the relationship is true in both cases, right? So a slinky's not as taut as a car spring, but the force required to stretch it is proportional to the distance you're trying to stretch it. Up to a point, and then the spring just breaks. But up to that point, this law of Hooke's holds. Okay. So when we stretch a spring, what does it look like? Like in our force displacement. So we've got our force on the vertical and displacement on the horizontal. Well, if F is equal to k times x, this would be like the x over here, right? So it's just k times x, so it's just a constant, right? It's just something like this. This is F equals kx. Right? K is kind of like the slope of the line, right? The larger k is, the steeper this thing climbs. Right? If k is really small, then it's a really flat line. If k is really large, it's a very steep line. Okay, so the required force grows, as you can see, the required force grows as the spring is stretched. So what does the work look like here? Well, it's again the integral from 0 up to x, however far you want to stretch it. We'll go from 0 here over to some value x, and it's going to be f times f dx, right? In this case, the case of a spring, the force is equal to this constant, spring constant, times x. Right? The force varies proportional to the displacement. Right? And we know that that's equal to, what's this integral, kx dx? It'll be 1/2 kx squared, right? Okay, and so the integral here would be 1/2 kx squared, right? So this would be, for a spring, the amount of work done in stretching it is equal to 1/2 kx squared. Okay, where x is the distance beyond the distance beyond the natural state that you've stretched it. Okay, if we look at this visual, right, we can easily see that this area, remember we said that work is the area of a plot like this. This area is in fact 1/2 kx squared. So this leg here is x. What's this up here? Well, it's k times x, right? Whatever x happens to be, that's how tall. And this thing is going to be k times x tall, right? And so that area, remember the area of a triangle is 1/2 base times height. So it's 1/2 x times kx, and so it's 1/2 kx squared, right? And so this just kind of confirms that the integral works, and that hopefully this is intuitive if you think about how springs actually stretch. Okay. All right. Perfect. Let's do an example. Okay, let's do an example. Simple example here. Let's say a man weighing 600 newtons steps on a spring which compresses 1 centimeter under his weight. Okay, so a man steps onto a spring which compresses 1 centimeter under his weight. Let's find K, the spring constant, and let's identify the total work done under this compression. Okay, so just to make sure it's clear that what's happening, you've got some kind of a spring which is in its natural state here, and we'll say that maybe there's some kind of a stepping spot on the top of the spring, and when the man steps on it, the spring compresses a bit, right? And we'll say that the amount it compresses is like 1 centimeter. So it goes from there down to there, and that equals 1 centimeter. Okay, so it just squeezes down a little bit. So then the question is, first of all, what's the nature of the spring if this is the case? And then second of all, how much work was done in compressing the spring this distance? Okay, so we know that force is equal to K times X in the case of a spring, right? And so the force here is 600 newtons. Let's make everything negative, so it'd be 600 newtons in the negative direction, right? So I've got negative 600 newtons equals K times X. Do I know the displacement? Yes, I do. The displacement is 1 centimeter in the negative direction again. So it'd be K times, I'm going to convert that to meters. So 1 centimeter is 0.01 meters. So negative 0.01 meters. Right? And so the spring constant is just kind of pops out of this. If you know the amount of force applied, you know the amount of displacement created, you can calculate the spring constant. So K must be equal to 600 newtons over 0.01 meters. And so when you do that, you get 60,000. Okay? 60,000 newtons per meter. Okay. All right. Now, so that gives you the spring constant, right? So this gives you some indication of how taut the spring is. Okay, so this is obviously much stiffer than a slinky, and it is obviously much less stiff relative to a car, right? So the car is 10 to the fifth. We said this was like, something significantly smaller. So that's the spring constant, right? So what about the work? Well, we saw that the work, we can think of the work as equal to the integral from x1 to x2 of f dx, right? And so that's the form. So let's plug in what we know. We know the integral goes from 0 to negative 0.01 meters. And instead of just f, we can put in our 60,000 newtons per meter, and we can say that's the force times x, right? So 60,000 so it looks like this, right? Okay, and so then we can integrate this. So we get 1/2 times 60,000 newtons per meter times x squared, right? And that's going to go from 0 meters up to negative 0.1 meters. 0.01, sorry about that, 0.01, yeah. All right, and can we just plug these quantities in? You betcha, right? So this is 1/2 times 60,000 newtons per meter. And then I'm going to go negative 0.01 meters. I'm going to square that, minus 0 meters. I'm going to square that. And so in the end, when I calculate all of these things, I'm going to get about 3 Newton meters, or 3 joules of work. Okay. All right. Very good. Very good. Okay, and so the amount of work done by this person stepping on the scale and compressing the spring is about 3 joules. Okay, so this is a nice example of, first of all, how to evaluate where does the spring constant come from. Well, you have to apply a certain force to compress it a certain amount, and that amount is proportional, as we've seen, as it's been shown experimentally. So if you just are given a spring and someone says, what's the spring constant, you can just you can apply a force that you can measure precisely, and if you can measure the displacement when that force is applied, you can calculate the constant. And then, of course, the work done is just the application of this formula we've seen. So the next question then is, so now that we know what work looks like when forces are variable, how does the work energy theorem apply when these variable forces are involved? Right, so we saw before the work energy theorem said that the total amount of work is equal to the change in the kinetic energy, right? K2, K1 being final and initial kinetic energies, respectively. So how does the work energy theorem play out when the forces involved are not constant? Well, we'll derive that in a sec. First thing we want to point out, because it comes up in the derivation, it's important, is to notice something about acceleration. So acceleration, this is an aside, so we're going to use this in a second. I just want to kind of lay it out ahead of time. Acceleration is the change in velocity over time, right? And so acceleration is equal to dv dt, right? And so we can rewrite this as dv dx times dx dt, which is to say that acceleration is the product of the change in velocity with respect to displacement times the change in position relative to time. Okay, and so all of this, as you can plainly see, is equal to dv dx times v. Now, where's this v? Well, that's just this, right? This is another way to write velocity. Velocity is just the change in position relative to time. All right, so this is important. We'll need this for our derivation. Okay, So let's jump to the work energy theorem. What does it tell us? Let's start with what is work when a force is variable. The total work done is equal to the integral from x1 to x2 of the force dx. Right, now we know that by Newton's second law, the force is equal to ma, so this is x1 to x2, and then it's ma times dx. Okay. And we can rewrite this as x1 to x2 of m, the mass, and now instead of a, I'm going to plug this piece in up here. I'm going to plug in dv. Well, I'm going to put it in a reverse order, but it'll be v, and then dv dx. And then remember, I still got the dx over here. So just replacing some of these quantities. Okay. And let's just regroup this a little bit from x1 up to x2, and then I've got mv, and then I'm going to put all of the dv dx business together here. Okay, so I want to talk about that. So what is dv dx times dx? So dv dx times dx, what is this? This is really just the change in velocity. This is just the change in velocity over the displacement dx. This is just the change in velocity over the displacement, which is just dx, dx, the change in position. Right, so what's another way to denote dv? What's another way to denote the change in velocity over the displacement? Well, it's dv, right? And so this is just dv. So this would be equal to, well, I'm going to write it, but then we'll see why it's wrong. Okay, so this part here certainly can be restated as this, but what's the problem with this? Well, here we're integrating with respect to position, x, and now suddenly we're integrating with respect to velocity. But my bounds on my integral have not changed. That's a problem. I can't go, I shouldn't try to plug in a position into a function that's essentially about velocity. So my bounds need to be rewritten, right? So instead of that, I'm going to write the integral from the initial velocity up to the final velocity of mv dv. Right? The nature of the integral changed, so I have to change my bounds. I can't use position. Okay. And so the total work, the total work is equal to this integral now. It's equal to the integral from the initial to the final velocity of mv dv. Can we integrate this? mv dv. M is just a mass, v is just the velocity, right? So yeah, we can definitely integrate. This is 1/2 mv squared between v1 to v2, right? And so we know that that's going to be 1/2 mv2 squared minus 1/2 mv1 squared. This is k2. This is k1. Final and initial kinetic energy. So this is the same formula as we saw previously, right? So this is the same formula. Well, it's the same equation for the work energy theorem. Right, so it works the same way. If you know the initial and final velocities, you can calculate and you know the mass, you can calculate the change in kinetic energy, and that's going to be equal to the total work. Now, just the only thing that's changed here is the total work itself is based on a force that may vary depending on where you're at in the displacement. But otherwise, it's the same setup. It's the same situation. Right? That's very nice. It's nice when these big theorems continue to work. Just as we make things ever so slightly more complicated, the formula remains itself. Okay, so let's do an example where we use this. Okay, let's do an example. So we'll say that a mass of 0.1 kilograms is attached to a spring attached to a spring on a horizontal frictionless track. Okay. The spring constant is 20 newtons per meter. Okay. Right, and we'll say that initially the spring is in its resting state, but the mass is moving to the right at 1.5 meters per second. So the spring is initially in its resting state, and the mass is moving 1.5 meters per second to the right. Okay, so what is going on? What's the picture here? Let's draw the picture, and then we'll get to what the question is here in a second. Okay, so I've got this, some kind of a contraption. It's a frictionless track. Then I've got a spring attached to the thing. And attached to the spring is some kind of a mass. Just call it mass. And it is 0.1 kilograms. Now, when we measure at the starting point initially, the spring is precisely in its resting state, which means there's no force being exerted on the mass in either direction initially, right? But the mass is moving at 1.5 meters per second, right? So an instant after this initial state, it's going to be a little further over, and at that point the spring is going to start stretching, right? So it's almost like it's just crossing the zero line, right? And it's going to start moving off in this direction. Okay. Now, as we kind of release the as we sort of move forward an increment of time, then the spring is going to start stretching. It's going to start to slow down the mass, right? And if we move a little bit further up in time, the spring will be stretching more, and it'll be exerting more force on the mass and slowing it down even more. Eventually, the mass is going to reach some spot over here where the spring has completely stopped it, and then it's going to reverse directions. Right, so that's kind of the scenario, right? And it's frictionless, so we don't have to worry about any friction coming into play here. So the question is, what is the max distance? What is the max distance the mass will move to the right? Right, because it's got a certain amount of kinetic energy here. It's a mass times a velocity squared, so 1.5 meters. It's moving. It's got some kinetic energy. That kinetic energy is going to get thrown into work being done on the spring. Eventually, that kinetic energy is going to drain out, and we'll hit K equals 0, and then the whole thing will reverse directions, right? So the question is, how far down the track do we get? So somewhere down here, there's a D. We want to know what is that distance. Okay, very good. So it's kind of a nice little question. It's got a kind of a seemingly complex setup, right? It's kind of a difficult thing to imagine how to solve if you didn't know anything about this kinetic energy and work concept. So here's the free body diagram. I don't know if we necessarily need it. It's just good practice to always create one. I've got the normal force. I've got the weight of the thing. Okay, and then the only force involved is the spring force. It's kind of pulling it back in this direction. Now, initially there is no spring force, but as I said, a moment later, a moment into the experiment, the spring is going to start to stretch, and it's going to start exerting a force. And that force is going to vary depending on how far out towards D we get. Way out here, the force is going to be really large. Here, just a smidgen off of 0, the force isn't going to be very large, but it's going to grow. Okay. All right, so what is the total work? So as the mass moves from 0 up to D, there is going to be some amount of work done on the spring. So what does that work look like? right? We just talked about this, right? We know that the total work done here is the integral from 0 up to d of kx dx. Okay, and so we know it's 1/2 kd squared. You can do that integral and you can see that that's the work. Now, actually, the work here is going to be negative, isn't it? Right? Why is the work negative? Can you see why the work would be negative? The work is negative because the force that's being done is opposite the direction of the displacement. So the displacement is to the right, the force is pulling to the left, so the work is negative. So this whole thing will be negative. Okay. All right. Can we calculate this value? Yeah, we know a couple of pieces of this anyways. Negative 1/2, we know K is what? 20 newtons per meter. And then we've got d squared. So actually we can't quite get to this yet, right? Because we know this is negative 10 newtons per meter times d squared. We don't know d. D is what we need to find. Okay. So we've got the one side of the work energy theorem, the work side. Now we need to kind of concern ourselves with the energy side. So what does the energy side of the equation look like? What about the energy side? Okay. So on the energy side, well, you've pretty much got these two positions, right? You've got the starting position and then you've got the ending position. So this would be like K1 and this would be like K2, right? So at K1, what's the kinetic energy? Well, it's 1/2 mv1 squared. So 1/2 times the mass, which is 0.1 kilograms, times the velocity, 1.5 meters per second squared. And so we get 0.1125 Newton meters of joules. That's K1. What about K2? So at K2, that's over here at D, right? What's the velocity of the block at D? It should be instantaneously 0, right? Idealized, instantaneously 0 when the block moves D from the resting position. So you should have 1/2 mv2 squared, which is 1/2 0.1 kilograms times 0 meters per second quantity squared, which would be 0 Newton meters. Okay. And so that's what the kinetic energy looks like. The kinetic energy is going to go from this down to 0. Okay. So then just kind of using the work energy theorem, we have W total equals K2 minus K1. And so the implication there is that W total is this thing, negative 10 newtons per meter times d squared. And that's going to be equal to K2, which is 0 Newton meters, minus K1, which is 0.1125 Newton meters. Okay, so remember we're trying to find D, right? So then we can just solve for D. D is equal to the square root of this thing divided by negative 10. So negative 0.1125 Newton meters divided by negative 10 newtons per meter. Okay, and when you do that division, you get 0.106 meters or 10.6 centimeters. Okay, so the distance that the mass will traverse before all of the kinetic energy is drained to 0 is about 10.6 centimeters. Right, so it's going to go about it's going to stretch the spring 10.5 centimeters, and at that point, all the kinetic energy will have gone from 1/2, m times 1.5 meters per second down to 1/2 m times 0 meters per second. So it'll slow down and come to a stop here, and then it'll reverse directions. Very cool, very cool. Okay, all right, so that's where I will we'll leave this one. The next lecture we'll talk briefly about the concept of power, but then we will have after that we will have a problems and examples section where we go through lots and lots of good examples of using work and kinetic energy together. All right. Till then, take care.